Ladies and gentlemen, welcome to Observing the Equinox with Griffith Observatory at local solar noon. That's right, we have a couple of celebrations for you today to celebrate the equinox. Today is the Northern Hemisphere spring equinox, or of course, the March equinox. It's actually the Southern Hemisphere fall equinox, and of course, we're going to talk a little bit about that. But let me introduce our program to you. I'm Dr. David Reitzel, and with me is Patrick So, of course, of All Space Considered fame. But we are very lucky today also to have a very special presentation from Griffith Observatory Director, Dr. Edwin C. Krupp. And it's going to be fantastic. Inhabiting the meridian, we're thrilled to be able to hear all about meridian arcs and the role they play and how Griffith Observatory fits into this. So welcome everybody to our celebration. Let me get it all started here for you. First of all, what is local solar noon and why are we starting after 12 noon? Well, a lot of you maybe have heard of things like high noon, or the famous movie here, Gary Cooper, High Noon. That was the time when the sun was as high in the sky as it gets for that particular day. It's heading from the eastern part of the horizon to the west, so high in the sky, and that's what we call local noon. And I'm sure our director will tell you a little bit more about that. This is different than clock noon, and it doesn't happen at 12 noon, as you know. This has a little bit to do with time zones, as you'll see here, and let me zoom in on our own time zones of North America. And as you can see, even our own Pacific time zone is very wide. So the notion that we all share noon at the same exact moment of time, well, the sun won't be directly overhead for anybody right there at that moment. So we are celebrating local solar noon today at a little after 1 p.m. Our presentation at the Meridian Arc will start before that, and Dr. Krupp's presentation will start today about 15 minutes after 12, so we're rapidly approaching that now. Now, first of all, I'm saying we're observing the equinox. If you're going to observe the sun, you need to do it safely. You either need to have some of our eclipse glasses, maybe if you purchased them for the last eclipse. If you still have your pair, make sure they're safe to use. But right now, we are using our instruments at Griffith Observatory. We are using our Meridian Arc in the Gottlieb Transit Corridor. And also tonight at sunset, we will use our sunset lines. So this is quite exciting for us here. Now, what is actually happening today? You might want to know. Well, it's the first day of spring for the Northern Hemisphere, and March 20th, as you can see in this diagram I'm showing you. You'd want to be looking in the back. Let me get my little laser pointer here. So over here, March 20th, this is the position Earth is in this very simplistic diagram of Earth orbiting. Now notice the tilt of the Earth remains constant as it travels around the sun. The tilt is pointed in the same direction. The net effect of this is that the sunlight hits different portions of the Earth and is more concentrated in the north during our summer. It's actually hitting us edge-on in springtime, and in winter it's hitting more obliquely. It's hitting more direct overhead for the southern hemisphere. And like I said, here would be an example of winter. We're coming out of this time. The sunlight is more directly overhead down south. It's very oblique up here. The sun is at a very large angle. This causes, of course, the seasons to change. It makes our winters colder. Today, on the first day of spring, the sunlight is hitting directly overhead on the equator. And you can see the Earth is roughly equally lit in the north and the south. And of course, as we head towards Northern Hemisphere summer, the sunlight will be more directly overhead for the Northern Hemisphere, and the Southern Hemisphere will have that very spread out light. And as you can see here, this effect has been seen, of course, and photographed in this really interesting little movie. I believe this is a click to play for me, so I should be able to do that. There we go. And as you can see here, the sunlight looks like the sun is going down south and now headed back up north, and then back towards the south again. But of course, this is the effect of the Earth tilting. The camera has moved along with the Earth in this example. So picking out the relevant dates, again, from some nice satellite imagery, you can see here that we have our first day of spring, our first day of summer, where the sunlight's more directly overhead. You have that 24 hours of sunlight in the Arctic Circle up here. Notice up here, as the Earth spins, you're never seeing the sun set. However, down south, down here, you never see the sun rise. Of course, over here, first day of fall, and now we're back over here to winter for us, and the Southern Hemisphere and the Antarctic gets the sun that never sets. This is something a cycle that goes back and forth once again. Now, a lot of folks might be confused. They think that the warmer days are caused by the Earth getting closer to the sun. This is actually not the case whatsoever. Patrick, you're here with us, and this is something that we were discussing the other day. When are we closest to the sun? It's on this diagram, but interestingly enough, it's in
right.
January, right? You got to unmute yourself, I think.
Yeah, it's just a couple of weeks after the winter solstice, around about December 21st. We're actually closer to the sun than we are, say, in July, where we're farthest from the sun. And the difference is roughly about close to about 5 million kilometers difference between the closest point and the farthest point from the sun. But even so, that doesn't make a big difference to the temperature, contrary to popular belief, where when we're closest to the sun, it seems to be hotter, or the distance isn't much of a factor compared to 93 million miles from the Earth to the sun.
Yeah, now, of course, there are systems where this does make a big difference. There are exoplanets around other stars, and when a planet gets very close to its star and then travels very far away, that's a different story. We see that, of course, with comets within our own solar system as they get very close to our sun and will heat up. But our seasons are caused by this tilt of the Earth like we've been talking about. Well, we have instrumentation here at Griffith Observatory to observe this. Of course, I should have set up at the top, and this is one of the reasons we're running a little ahead. I'm so excited about today's program, but Griffith Observatory is operated by the City of Los Angeles and the Department of Recreation and Parks. So we are very lucky to have this sort of instrumentation available to Los Angeles, available to people visiting Los Angeles, can come up and take a look, observe the sun safely with what we have here as our public instrumentation. We have staff on days we're open to guide you through the experience, of course. But today we have our very own observatory director, Dr. Krupp, to tell you a little bit more about our Meridian Arc, which is in the Gottlieb Transit Corridor. Dr. Krupp, take it away.
Well, thank you very much, Dr. Eitzel and Mr. So. And obviously, thanks everybody for tuning into live Griffith Observatory television and observing with us the vernal equinox. And I remind you, as Dr. Eitzel just has mentioned, this vernal equinox is brought to you absolutely free by the City of Los Angeles Department of Recreation and Parks and Griffith Observatory. And on top of that, of course, we are supported by our nonprofit 501c3 organization for support and advocacy. That is the Griffith Observatory Foundation, which helps us on many specialized tasks. I, of course, remind you, as has already been the case, this is the first day of spring. And as a prelude to local noon, which has just been described, we'll spend a little quality time with the Meridian, which is inextricably linked with local noon. And so we'll, in fact, ourselves be kind of inhabiting the Meridian as others have in the past, and as instruments that are organized to perform astronomy kind of do all the time. Now, the Meridian, of course, is a fundamental reference in our system of direction. It is just the line that runs on the ground from true north to true south. And in fact, that's a meridian right there. That happens to be the meridian at Greenwich, England, the prime meridian laid out on the stone in metal there. And so wherever you go, there you are on some local meridian. It doesn't have to be Greenwich. And many monumental antiquities were actually intentionally aligned with it. The whole idea of course, of north comes from the movement of the sky. We wouldn't have north if the sky didn't seem to rotate, which is, of course, the spinning Earth. And it creates that one spot in the sky that does not appear to move while everything else seems to circle around it. Well, when you're facing that direction, you're facing north. That's what north is. And again, without that, we wouldn't have it. But we do have it. And we've made a habit of incorporating it into all kinds of tools that we rely upon to orient ourselves in the landscape and to make things happen. It is, of course, incorporated into maps. This is just a map of Washington, D.C. And the map indicates, of course, that north is at the top, south is at the bottom, and east and west are on either side. But those maps and directionalities extend very often into the very plans of cities. Now, not every city is organized exactly north, south, east, west, but an awful lot of them are. It's been a habit we've had for a long time. This is just the grid plan of Chicago, Illinois. And as you just even glance at the map, you can see that the streets are orthogonal and they go up and down and left and right. And they do adhere to the cardinal directions, which again originate in the motion of the sky, which really is rooted in the local meridian. And even Griffith Observatory, of course, is oriented cardinally. And so as we look straight down on it, the north-south line is just the vertical line in the picture. The east-west line is any of those horizontal lines that would be going from left to right. So the meridian then, as we've seen, does in fact originate in the behavior of the sky, a fundamental astronomical reference, and probably most familiar to people, as we have already seen, as the prime meridian of the world at Greenwich, England. The Greenwich meridian serves as the adopted 0 point for longitude on Earth. So when we measure longitudes to establish positions around the Earth, those positions now, by convention, begin from this location. And of course, it's got its obvious use in all kinds of practical things. But if you go to Greenwich, people just do just about everything with the meridian. They stand on the meridian, they sit on the meridian, and in fact, they even observe on the meridian. Again, a concept that is rooted in the behavior of the sky, that north-south line, all given us by that fundamental motion of the Earth, the daily rotation. So thanks to the spin of the Earth on its axis, we see, say in a time exposure like this, we see the trails of stars recorded on a camera's sensor. And that picture with all of those trails of stars over time looks like that might be about a 20-minute exposure or so. With all those little segments, they look like complete circles, but they're all circling around the north celestial pole. That's just the point straight above the Earth's North Pole. And of course, the Earth's North Pole is just that point on the north half of the Earth around which the Earth turns. That is, through which the imagined axis of the Earth is going. So we've got this business then of the Earth's rotation giving us north, the fundamental motions being evident in what we see in the sky. All of this really just due to that great celestial soap opera. As the world turns, we see, in fact, the sky turning, and we get these fundamental directions before us. And as mentioned already, the key thing about local noon is that it is the point when the sun and its daily course across the sky crosses over the north-south line and reaches its highest point in the sky for that day. That is its transit point. And in this diagram, an imagined, of course, view of the universe from antiquity, in a sense simplified, centered on the Earth. If you look very carefully at that Earth, we've made it so it's actually centered on Los Angeles as well, but that's not really the way the universe is put together. It's still an easy way to look at how the sky works. And so we're sort of outside the sky with the Earth inside that sphere and the sun over there on the right, rising as it does, of course, at the point where the day begins, arcing up and higher, crossing the celestial meridian at local noon, and then setting over there in the west. Well, this is a common principle. And in fact, we find it everywhere. You can pick up any standard astronomy, monthly astronomy magazine like Sky and Telescope. They'll publish a star chart like this one. And there's a thin blue line running right from the top of this diagram to the bottom. The rim is the horizon, but that thin blue line that cuts it in half is the celestial meridian. And that's just the astronomical concept about which we are talking, again, established by that fundamental motion of the sky. So as this kind of thing takes place, of course, we realize, yeah, you got those stars performing trails around the North Celestial Pole, but it really is distinctive when you face the opposite direction. When you turn around and face south, the stars and any other object are still traveling in what appear to be circles around the sky. But because of the geometry and your position on the Earth, those circles look very elongated. They don't look like straight lines, but they look a lot closer to straight lines. And so this distinction of the difference between the way the sky behaves in one direction and then in another direction, and the fact that there's a spot in the sky that seems to be still while everything else moves, was a lesson not lost on all of our ancestors. Everybody picked up on this kind of thing. And just to show you a couple of examples of this sort of thing, we can go out here in Southern California, out into the local mountains, a site called Alder Creek. Now, this is a natural rock shelter where Southern California Indians, the Chumash in particular, painted. It's not an observatory, it's a shrine, a sacred shrine, but it happens just by chance to face directly north. And when you're looking out the shelter there, you're looking straight north. If you look up on the ceiling, it's possible to make out a number of the images that were painted up on that ceiling. And those figures are all related to the function of this as a shrine for shamanic activity. But at nighttime, if you look out that same location, out that window, you can see that it is roughly oriented on the pole. That's the pole star right at sort of the center there. And this time exposure shows some of those star trails going around it. And interestingly, this particular shelter's floor and roof are slanted in a way that it actually points up to the pole, and there's a natural crack in that boulder on the ceiling that forms a natural line that is also pointing out to the north. Now, this is all accident of nature, but the fact that it was incorporated into a shrine this way with all of these little creatures painted there, and they all seem to be heading out to the North Celestial Pole, up that ceiling, up that direction, because that place was regarded as a place of celestial power, particularly because of its distinctive behavior. Well, people all over the world have recognized this kind of thing. You can go to the American Southwest, to Chaco Canyon. The prehistoric Pueblo people built extraordinary structures, stone structures in the northwest part of New Mexico. This one is Pueblo Bonito, and it in fact is organized on a north-south line. You're looking at that line from north to south right now. And we can tell that that's the case. You just look at a plan of Pueblo Bonito, and you can see that there is a sort of a split in the two sides of it, a vertical line. That's the north-south line. And it's a wall, actually, a meridian wall that is built that splits that plaza into two, with a big ceremonial kiva on one side and another ceremonial kiva on the other, but very deliberate design in this prehistoric architecture. Beijing in China, this is the only world capital that still adheres to an ancient cosmological plan. You're looking now along the primary meridian of Beijing and the imperial palace, or the so-called Forbidden City. In a plan, you can easily see that this architecture was all oriented and very deliberately north to south. And it too is recognizing the fact that you've got this aspect of the sky being brought down to earth into the architecture and relying then on the meridian to do it. The reasons for this, though, are not astronomical observation. It takes astronomy to do this, to map these things out. But here in the People's Republic of China, in an earlier era, in the imperial era, during the Ming Dynasty, this was laid out deliberately in order to focus the political and spiritual attention of the government onto the emperor, who carried out all of his activities, his formal activities, essentially at the center of this structure, at the Hall of Supreme Harmony. And here you're just looking right along the meridian that runs through the Imperial Palace, going straight to the Hall of Supreme Harmony. And the meridian is really laid out in the walkways and the stairways. In fact, to get there, you actually do walk and follow the meridian. Now, not everybody went into the Imperial Palace. This was strictly for the rulers and the bureaucracy, but they all were focused and in a sense circled the emperor in much the same way that the stars circle the North Celestial Pole. And the emperor was regarded as the counterpart on Earth to the hidden face of Shangdi, the supreme lord of the universe, whose face could be seen in this sense symbolically in the sky. Shift to Egypt, and in fact, the pyramids of Egypt are also all cardinally oriented. Here, in fact, you do have monumental tombs that were built for the pharaohs that reigned and had them constructed. But looking, in fact, at a plan of Giza, it's easy to see that it adheres to the cardinal directions. All of these pyramids are, in fact, intended and conform to north, south, east, west, and again, rely on the origination of those directions. And the Great Pyramid, part of the reason it's great is that it is actually so very accurately organized and aligned to the cardinal directions. The worst error in alignment is about 1/5 the size, that is the diameter of the full moon. And all of the other sides align even better. And what's even more remarkable, it's not just that they were able to lay out those lines, but then build that thing up to 481 feet high and keep it true. That's not easy. Shifting back to China, just to demonstrate, though, that these observations and these kinds of constructions are really rooted in astronomical activity. This is the observatory of Guozhou Jing, a 13th century astronomer in China. He was probably doing the best astronomy in the world in the 13th century, built a number of observatories. This one is in north central China. And it has, as you can see, a tower, and there is a long sort of wall extending out from it. Well, that wall was really like a measuring ruler. And if you think of the tower as sort of a shadow caster, and it was, the difference between a high sun in summer near the top of the diagram and a low sun in winter will send a shadow along that wall to two different places. And in fact, through the year, all kinds of different places in succession along that low wall. Looking, in fact, from the top and looking now to the north, this is the view down to the wall on which those shadows would be cast. And in fact, those observations enabled Guozhou Jing to establish, at least for his time, the length of the year more accurately than anybody else had done before. All of these principles were applied much more elaborately in the 14th century by an Islamic astronomer and ruler, Ulugh Beg of Samarkand, in what is now Uzbekistan in Central Asia. He put an arc on his meridian to observe transits of the sun and other objects on behalf of timekeeping and calendrics and star mapping. Well, in the diagram, you can kind of see the structure that he built there. We know this from historic sources. It was a kind of a cylindrically shaped building with this meridian arc running right through the middle, bisecting it on the north-south line. And then as the objects were either sighted from below or had, in the case of the sun, light projected, they would shift their position if they were moving like the sun, or they would stay in position like a star to enable, through timing and measure of angles, the mapping of the heavens, which is exactly what was done. There's not much left of Ulugh Beg's observatory any longer. It's remarkable that any of it is left at all. But part of that meridian arc survives. It actually continued underground and was excavated around it, buried eventually over time, but has been then re-excavated now. And if you visit Samarkand, you actually can see that those remains of the meridian arc looking in one direction and in the other. And just to get an idea of how it was used, a variety of observations be made, but this is just the projection of a beam of sunlight from up above falling down onto the arc, which is inscribed like a ruler. And then you have individuals, astronomers at work, making measurements, very careful measurements from day to day to see exactly what that angle is, and in order to use that both for timekeeping and for calendar, and of course, ultimately for other applications of the sky. Europe developed its own calendrical revelations in architecture with giant meridian scales that were installed in churches. At first, these were intended just to monitor the progress of the year calendrically, but these meridianas were eventually inscribed on church floors by astronomers, particularly in the 18th century, to make precise measurements of the sun's daily noon elevation. So the astronomers invaded the churches with astronomical instruments because the churches had great big rooms in which they could build the instrument to cast the shadows and send the spots of light that they wanted done. The particular instrument that you see here is a design that was put together by Ignazio Dante for San Petronio, a cathedral, a basilica eventually in 14th century Bologna, Italy. He designed this in 1575. And the idea is that you have a tower there on the left. There's a hole up there. Sunlight passes through the hole and then sends a spot of light down to the horizontal line on the ground, which is inscribed like a ruler. And of course, in winter, that shadow or that light, that beam of light is thrown a great distance. In summer, when the sun is high, it's a short distance. But because of these differences, you can, in fact, keep very careful track of the passage of time through the year. And the bigger you make this instrument with appropriate modifications, the more accurately you can determine these values for the time it takes the Earth to go around the sun. And also the better and better calendars, which of course is the real goal in this case. Well, Dante never finished that Meridiana that he planned for Bologna, and it was replaced in 1655 by a grander Meridiana designed by the astronomer Gian Domenico Cassini. Cassini's 220-foot meridian is still embedded in the cathedral stone floor, and you're looking along that meridian line right now to the south, and if you look very carefully up the wall and almost to the top of the picture, there's a tiny little sort of dark spot. That's actually a window in the wall through which the sunlight can pass. And a close look at that window shows you that they have designed a kind of a solar disk, a ray disk around the hole to symbolize the sun. Well, that's looking at that meridian line in that direction. And of course, you can look in the opposite direction where it continues and makes it possible then for the sun to fall on that line, casting a spot of light that then can be used, often in conjunction with some other auxiliary instruments, to get the precise measurements desired. This happens to be, by the way, the sun shining into San Petronio on the 18th of November in 2004. There are quite a few of these meridianas around, particularly in Europe, a lot of them in Italy. Just for the record, here's another one. This is at Bergamo in northern Italy, and it's operating like clockwork on the 14th of October 2009. Of course, formal observations of the sun's meridian transits persisted in national observatories like the Paris Observatory, the cornerstone of which was laid on the summer solstice in 1667 and during the reign of Louis XIV. France adopted the axis of the Paris Observatory as its preferred meridian. And Cassini was invited to Paris to assist the development of the new Paris Observatory, became the first director. And extending this inquiry he had undertaken at San Petronio, he constructed a large meridiana in the Great Hall on the second floor of the Paris Observatory. This one's about 96 feet, 10 inches long. He wanted the building to perform as an instrument, and he designed his meridiana to coincide with the meridian of France. And in fact, the meridian just continues outside the observatory. They've got it laid out on the ground. And of course, it was not just an astronomical enterprise, but there was a fair amount of national priority built into the notion of establishing a meridian. And with this, Cassini planned to obtain a more precise determination of the apparent annual motion of the sun. Well, despite the French predilection for a French prime meridian, the local Greenwich meridian, occupied by George Airy's transit circle of Astronomer Royal in Britain, was officially adopted as the prime meridian of the world in October 1884 at the International Meridian Conference held in Washington, D.C. And Airy, in his transit circle, then he used in the service of British cartography, but the old observatory had been established, in fact, in 1675 by King Charles II. He wanted it dedicated to finding out the longitude of places for perfecting navigation and astronomy. Long before that ever came to England, however, and Airy's transit circle, the people in India were working on their own meridians. And in fact, in medieval India, a stake was claimed for the prime meridian through the town of Ujjain, which is about 400 miles south of New Delhi. It's in central India, and it was believed to occupy the Tropic of Cancer, and that in part accounts for its status, and its instruments, again, are aligned there. But this observatory that was built there was, in fact, intended to be seen as the site of a prime meridian for India. Sawai Jai Singh II, who was the Rajput ruler of Jaipur, he's the one that built Ujjain in 1730. And he built 4 more monumental observatories, and his most elaborate is in Jaipur. And there, the great Samrat Yantra that you see here makes sculpture and architecture out of an instrument. You're looking up the stairs, and in fact, you're on a meridian again on the north-south line. This place, though, this instrument, monumental instrument, includes a very interesting component. It's a cardinally oriented room. There's the entrance to it, that houses a pair of inscribed quadrants and permits light from the transiting sun. You can see one of those arcs, meridian arcs, on the right side of the picture. And then as the sun gets close to local noon, its light passes through a couple of holes in the upper wall. Right now, the one of those holes is visible, and the light hasn't quite reached to the arc. It's just bouncing off the wall to the side. But there now you see both of those 2 pinholes up in the wall, the light, and then eventually those pinholes of light, projected light, fall on inscribed scales, the 2 arcs on one and then the other, and those permit then very accurate measurements of the position, the angle of the sun on that particular day, and so continue the process of establishing calendar and time. Well, there are all kinds of meridians around the world, but anyone who collects meridian markers now, of course, has to navigate of course, to Los Angeles. Griffith Observatory, as you've already seen, is cardinally oriented. It faces north, and its telescopes are aligned with the North Celestial Pole to facilitate continuous tracking of celestial objects. The Gali Transit Corridor, visible here, is part of the observatory's renovation and expansion that was completed in 2006. So this is a completely new component of Griffith Observatory, and there really is nothing else like it on the planet. But the observatory it has adhered to cardinal orientation from the beginning. And again, it's echoed in its instruments, as mentioned a moment ago. The Zeiss telescope, of course, even the sundial has to be oriented that way, as does the solar telescope. The transit corridor, though, is the place where most of this now gets focused and where we'll be moving in just a short time. The Griffith Meridian is really part of this singular and monumental instrument, and it's about 150 feet long. That is the entire structure, not just that metal arc that you see in the foreground of the picture, but the instrument is really the entire architectural space on the west side, where these parallel glass walls, 150 feet long and 20 feet high, preserve below grade the observatory's signature vista of the western horizon. And this instrument just demonstrates how the sky works through meridian transits of the sun and the moon and the stars over the walled corridor. And the corridor, about 10 feet wide, is bisected by the bronze meridian line that is set into the concrete floor. It extends the full length of the walls, which then frame the celestial meridian. If you're in this space and you look up, you see a line of sky over your head, and that, although larger than a single line, does in fact echo the celestial meridian arc that's going right over your head at that time. And so the structure really turns an astronomical abstraction into a personal visual experience for every visitor. The architecture reveals the astronomy. Well, at the north end, the meridian line, well, you're looking now from the north end to the south and reestablishing the line. But if you look from down below up to the north, you're looking up the banister. That stairway is angled exactly at the angle of the north celestial pole. So if you're down there at night, you can sight on the banister and see it's aligned with Polaris, the North Star, which in fact is right up there in the picture. And the observatory, of course, is engaged in all of this because of its fundamental character. And that's indicated right on the front of the building where the bronze letters declare Griffith Observatory. It's an observatory, and it puts visitors eyeball to the universe. Griffith Observatory is a public observatory, and the building's filled with instruments. All of them deliver real data and real experiences, and they transform visitors into observers of nature and the sky through instruments. So at Griffith Observatory, we are mobilized by the concept of the building as instrument, and the Gottlieb Transit Corridor is just another dimension of that immersive encounter with the sky. And there is more to it, though, than the long glass corridor, the north stairway, and the bronze meridian line. At the south end, a tall and night black monolith supports a stainless steel foil. And the foil on the ground has, and that monolith has just in front of it, the massive and bronze and stainless meridian arc. And above it, on the inside face of the glass wall, just to the left of the meridian arc and up high there, is mounted a huge and heavy ecliptic chart. That is a chart of the stars that straddle the ecliptic, the path through which the sun seems to move, and the planets and the moon, for that matter, over their course. Well, all of that combines, in fact, conspires to produce a demonstration of local noon by having a projected image of light, such as we've already seen elsewhere, fall on the Griffith meridian and on its meridian arc. A close-up of that meridian arc shows that it too is inscribed accurately and precisely with the days and the months of the year and the zodiac constellations that happen to accompany those through which the sun is moving at that time. And of course, when the sun crosses that meridian arc at local noon, it gives you a hint of where it is in the year you are, because you just read it off of the ruler. And people wind up going there every day, watching this happen from up above or inside the meridian. And you know, Tycho Brahe did all this in his own observatory in Uraniborg on the island of Hven in the 16th century with his own meridian arc and his own observatory. So we had to kind of surpass that. And we wind up now linking the meridian arc and the solar passage at local noon to that ecliptic chart, so that when the sun's disk approaches the center line of the meridian arc, it's first beginning to encroach there now, and then it starts touching and crossing over. And when it hits that, those little black dots are really sensors connecting up to the ecliptic chart, which lights up the location at that moment in the sky where the sun happens to be, and lights up the stars of the constellation that the sun is occupying. Those stars are invisible in the daytime, but at Griffith Observatory, they are revealed daily at local noon with the Gottlieb Transit Corridor. So the meridian really is a place and a time and a direction. And when visitors arrive at this junction of the sky, they occupy a place where space begins. It's kind of a cosmic modem that downloads the sky. They connect what happens in the sky with place and time and direction here on Earth in a dramatic, precise, and a content-rich revelation in light. The meridian is then not just an instrument or a concept. It is a stage, and the universe performs on it daily. And I'm headed out there now for local noon.
Well, thank you so much for that, Dr. Krupp. That was fascinating. And folks, don't forget, this is not done yet. Dr. Krupp is headed out to the Gottlieb Transit Corridor here at Griffith Observatory, and we're going to observe the sun transiting on our meridian arc, on the Griffith meridian. So this is actually very exciting. Now, Patrick, I assume you, like me, have seen many of these, and I particularly like to go down and see it transit on my birthday, and of course on special days like the equinoxes. Which is your favorite, Patrick? Oh, I think you're still muted, and this of course happens. This is our modern times here.
Yeah, sorry about that. Yeah, there's a lot of interesting things that happen during the year, and these seasonal ones are quite the ones that we take note of. Spring equinox is kind of my favorite. Actually, it's my birthday tomorrow, so so I consider myself as a spring person, and spring into the spring season, and then of course we have the summer solstice coming up as well, and then followed by the autumn equinox, and kind of interesting.
Absolutely. And as Dr. Rupp makes his way down to the meridian arc out there, I'm going to go back to the slideshow if we can here briefly. I want to show off a couple of interesting things about today. And that's where he's headed, our meridian arc. Now, of course, this is that the ecliptic chart that we were talking about. And that curving path you see on it is indeed the ecliptic. That's the apparent path the sun will take throughout the year due to the orbital motion of the Earth going around the sun. Now, today, the sun has a very special position in the sky, shall we say. You can see here that on the left-hand side, you can see our Earth embedded in the middle, that north celestial pole that Dr. Krupp was telling you all about, and how it is indeed projected off of the north pole of the Earth into the sky, the south celestial pole, and then of course the celestial equator, which is nothing more than the Earth's equator projected outwards into the heavens. Now, off to the right-hand side, we've created what's a coordinate system to track objects. Of course, if I'm an astronomer and I discover something new in the sky, well, if I were an astronomer, I am an astronomer, what am I talking about? Let's say I discover something in the sky and I want to share it with my colleagues. I need to tell them where to go look. So on the right-hand side, you can see how we've defined our coordinate system. There's a point in the sky that's on that equator called the vernal equinox, and we've defined that as a 0-0 position. And then we march off one direction along the equator that defines the right ascension, as it's called, and then you kind of march upwards in something called the declination to get the position of that star. Well, today, in a very interesting way, of course, today the sun is actually located right at that position of 0-0. So if I come over to it, here's our sun. Well, it's in the south. Here's our equator. It's in the southern hemisphere, and it's headed off into the north. Today, the sun occupies that position of 0-0, which is marked by the symbol there for the vernal equinox. So we can all celebrate knowing the coordinate of the sun today. It's at our central. It's at the origin of our celestial coordinates. So if you ever hear astronomers trying to define what's in the sky, and if they give you an altitude and an azimuth, that only works for, well, pretty much one location on the Earth. Anywhere else, it won't match up. You won't be at the right height. But this coordinate system works for everybody on Earth because it's reference to a position in the heavens and reference to the North Celestial Pole. So when you hear us talk about those, that's what we mean. So we can go back just to our view right now, our hosts, as we get ready for Dr. Krupp getting down there to the meridian arc. And as soon as he's ready down there, if we want to get a view, well, we'll see what happens. So folks, we can turn to some questions that I saw down in our chat. One person wanted to know, why does the Earth's axis maintain the same direction as we orbit the sun? It has to do with the fact the Earth is spinning. It's gyroscopically stabilized is one of the reasons. So you can picture like a gyroscope you set going. It'll maintain its direction fairly well. Now, if it's tilted off of gravity, it will wobble. It'll what's called precess and wobble around like that. And you might wonder, why doesn't the Earth do that? Well, the answer is the Earth does do that. The Earth does precess, but it takes a very, very long time for that to happen. I'm trying to remember the precession rate of the Earth. Do you remember it? Is it 26,000 years, Patrick?
26,800 years.
Yes, yeah, so
that's a long time.
a very long time, and currently the North Celestial Pole is located very close to Polaris, a fairly bright star in the sky, but not nearly the brightest in the heavens whatsoever. But that North Celestial Pole, if you wait long enough, thousands of years, it inscribes a circle in the sky, and it will track around and go through various other stars. Patrick, do you know what one of the next bright stars is that it's going to be pointed at?
Oh, okay. So in 13,000 years from now, the closest star to the North Celestial Pole will be the star Vega in the constellation of Lyra and a half.
Yeah,
and that's
exactly.
a much
So
brighter
that
star.
bright star.
Yeah, it's much brighter than the Polaris.
Yeah, much, much brighter than Polaris, which is very interesting. Now, the South Celestial Pole, there's currently not a bright star located there. And what's interesting about the South Celestial Pole also is the stars down there, for whatever reason, there's a lot of what's called proper motion. The stars are speeding through the heavens, so it's not as simple as what direction the pole will be pointed. The stars themselves are kind of moving around down there, so it's a little bit more complicated than simply knowing which one's going to be up next. Let's see if we have any other questions here in our chat that we can turn to. Of course, I've now misplaced my chat window when I realign things. There it goes. Some folks wanted to know, what's the best observatory near Washington, D.C.? I know that is the Smithsonian Astronomical Observatory, do they have a public branch there in D.C.? I know that there's the museums are there, Air and Space. Do you know, Patrick, or does anybody on our chat know? Patrick might be Googling it. I'm not sure. Patrick, you spent some time, at Adler? But that's up in Chicago.
That's right. Yeah, I spent a few years working at Adler before I came to Griffith Observatory. They do have a public observing program. In fact, they have their own telescope, which is a 20-inch Cassegrain telescope in the Northern Observatory, just kind of out there close to the Lake Michigan.
Yeah. Now, does that observatory have any alignments with North, or is there any sense of it being having sort of built-in instrumentation like our very own Griffith Observatory?
You know, I don't actually recall when I worked there. The observatory, the Doan Observatory, which is just off of the main building, is situated due east, and that's one thing I remember about it. But no, I actually I don't know if they even have they may have I'm not sure if they have a sundial over there.
Yeah, I'm not sure either, although you being not sure might say enough right there. At Griffith Observatory, we make our instrumentation part of the public experience. I see Jim Mann on the chat there and was saying maybe the U.S. Naval Observatory. I've never been. That is a great, wonderful facility, of course, that does wonderful work. A long tradition of observing the stars in the heavens and things like equinoxes by the Navy. If you were out on the open seas, back in the day, that people used instrumentation to sight the location of the sun, to measure the transit, to measure local solar noon. Depending on how that compared to your clocks on board, that would tell you your longitude. The latitude's easier to get. You measure the height of Polaris, or you measure the height of some known objects. But to get your longitude, your position east-west along the globe, people would actually use things very much like the transits here at Griffith Observatory. Now, I see we're just about the time we should be turning to Dr. Krupp. So if we're ready down there and we have a signal, I think we could turn it over there. If our switcher wants to switch over to our outside shot to let me know we're good. Otherwise, Patrick and I can keep entertaining you with random equinox knowledge, of course. There's Dr. Krupp. Turning it over to you, Dr. Krupp. Take it away.
Observatory's Gottlieb Transit Corridor on the west side of Griffith Observatory in Los Angeles, California. And we're dodging the clouds on the vernal equinox, anticipating local noon and the transit of the sun on the transit corridor's meridian arc by which I am standing right now. Just keeping track of time again, has been mentioned already. It seems perhaps a little bit odd that we're going to be observing local noon at what looks like very close to 1 p.m. on the clock here in Los Angeles. And of course, there are three things that affect that actual time and keep it from being the big hand and the little hand both on the 12 for local noon. First and foremost, of course, and the easiest one to understand is that this is daylight saving time. So we're already an hour off of what the standard clocks would be saying, but a standard clock keeps standard time, and that time applies to a time zone. And so, for example, the Pacific Standard Time Zone extends over quite a range of geography, far more than just Griffith Observatory or Los Angeles. But every location in that time zone has its own local noon because it's displaced either to the east or to the west of every other location. And so that, too, will alter the time of local noon compared to what it reads out on the clock. But finally, and maybe most extraordinarily, we're seeing here an effect of something nobody really ever has much of a sense about, and that is the fact that the Earth's orbit is not really circular. It's an ellipse, and that means sometimes we're closer to the sun and sometimes farther from the sun, and that means we sometimes move more quickly in our orbit and sometimes move more slowly in our orbit. Those things as well change how it is that we see the hands on the clock counting up when, in fact, an object like the sun is transiting. So local noon, then, is perhaps almost any particular time on the clock close to noon. And for us here in Los Angeles today on the vernal equinox, when the hours of sunlight balance the hours of night, will be just a little after 1 p.m. Well, one more thing about the meridian and the time that's important to keep in mind is, in fact, what time is it really on the clock when you count this out? And when we talk about 1 p.m. or 11 a.m., we're talking about the position of the sun with respect to the meridian. A.m. means ante-meridium. That means before the meridian. P.m. means post-meridian. That's after the meridian. The sun is to the east of the meridian at a.m. and it's west of the meridian at p.m., but at noon it's not on either. There is no such thing as 12 a.m. or 12 p.m. There is only 12 noon and 12 midnight. And we're just about at the point of local 12 noon, closer to about 1:01 p.m. Pacific Daylight Time. Well, the Griffith Observatory Transit Corridor includes a number of primary components, not the least of which is the corridor. And the corridor is established by the glass walls on either side of me, about 150 feet long, 20 feet high, and those establish the north-south line as well, with the meridian line laid out in metal, in bronze, that just continues all the way down to the steps at the north end. And those stairs, as I mentioned before, ascend toward the sky at exactly the angle of the north celestial pole, the pole around which all the stars seem to turn, all because the Earth is turning in its course of daily rotation. But if you come to Griffith Observatory at night and sight along that banister, you'll see the North Star, which is very close to the north celestial pole, right along that banister line. So you've got the corridor, which establishes the north-south line, the meridian, but there are a few other components that make this element work. And one of them, of course, is just in front of me on the other side here. There's the large, dark monolith of stone that continues high up to stainless steel foil. And the stainless steel foil incorporates an extraordinarily complex and very difficult to explain element, the hole. The hole allows light of a celestial object to shine through and then strike somewhere in the corridor, and then as the sun in this case is moving closer and closer to meridian, that spot of light moves closer and closer to this other key component, the meridian arc. When we get close to local noon, that disk of sunlight will begin to appear on the meridian arc. And the meridian arc then is, again, in stainless and gorgeous bronze, but it is inscribed with the months of the year and the days of each month, and also there are fine little elegantly drawn pictures of the zodiac constellations that correspond to where the sun is located, what stars the sun has in the background when it's in that part of the year. And over the course of the year, then, the sun continues up the meridian and down the meridian as it crosses. The highest time for the sun is occurring then in summer. Everybody knows the sun is high in June at the solstice. And way up at the other end, we have the point where the sun is going to be seen at winter solstice. And that winter solstice, the sun is low in the sky, and so you get a long oblique angle, but also with the disk of the sunlight hitting that point up there. In between, it's in between. And of course, right in between is the equinox. Two equinoxes, one, of course, in spring today, and the other in fall. And that's marked by this point right here. So, given what we've seen so far, you would say this is really kind of remarkable. At Griffith Observatory, we have managed to incorporate some Stone Age astronomy with some Bronze Age metalwork, a little bit of Renaissance ornamentation, and you could reasonably ask, is that good enough for the 21st century Griffith Observatory? And the answer is no, it's not good enough. But we've gone a step further. And that step further involves the chart of stars that is up above the meridian arc on the west side. That chart of stars maps the course of the sun through the ecliptic stars, that is, the stars of the zodiac constellations, over the course of the year. And it is connected electronically to the meridian arc. And so when the disk of the sun actually comes onto the arc and gradually moves across the arc, it will encounter these sensors. There are sensors that run all the way up and down the arc, but those sensors then signal with the sunlight that is shining at that moment to the chart up above exactly what stars are up there that the sun is occupying now, even though they're invisible, and also the position of the sun among those stars. We are, I said at the beginning, we are dodging the clouds today on the vernal equinox, but in fact, we have, for a moment at least, the image of the sun, and the Griffith Observatory guide is standing by just in case the cloud puts us out of business and we have to do a completely elegant simulation. But so far, so good. The spot of sunlight is moving closer and closer to local noon and the meridian arc's center line. It's encroaching now, just beginning to get to the sensors. A moment of high astronomical drama. And up on the ecliptic chart, there's been sufficient sunlight to capture the signal, and so you can see that the sun is located in the stars of Pisces the fishes. That's where the vernal equinox position of the sun is located, and the stars of Pisces the fishes are also illuminated at this time. Both of those will remain illuminated as long as the sun continues to shift through the sky and this spot of light moves across the meridian arc. Once it passes the sensors, then, in fact, it's over. But as you are watching this disk move right now, you are seeing the Earth turn before your eyes. Sun is continuing to move west of the meridian, the spot of sunlight moving east and getting close to moving off of the central line in the sensors. And once it moves off the sensors, the lights on the ecliptic chart go out. Ladies and gentlemen, welcome to vernal equinox, the first day of spring at Griffith Observatory in the Gottlieb Transit Corridor. I remind you once again, this vernal equinox local noon is brought to you absolutely free by the City of Los Angeles Department of Recreation and Parks and Griffith Observatory, and of course with the able and extensive assistance of the Griffith Observatory Foundation, the advocacy and support organization that works hand in hand with the observatory. Thanks very much, and back to Dr. Reitzel and Patrick So.
The advocacy and support organization that works hand in hand.
Dr. Kropf, that was fascinating. In fact, I need to mute things here, of course. And I'm a little behind on what we were doing there due to the time delay, so thank you for bearing with us there after Dr. Kropf finished up. That was fascinating, incredible to see. This is the very first time we have streamed Local Solar Noon live over the internet. So thank you to everybody that joined us here today to see this wonderful event. It really is something to behold our instrumentation doing what it does and bringing that to you live to the globe. So thank you so much for joining us. We have a little bit more we can talk about today in our final moments. Our program that you saw today, let me back up here a second. That one's set to autoplay. Our program that you saw today, actually some of the instrumentation we bring to our school kids that are coming and visiting Griffith Observatory virtually in our new online school program. We're currently piloting this school program. It isn't in full opening yet. We've been running it in testing phases, but we are, this is something we've been looking at and have tested in front of several thousand kids already, and we'll do some more piloting of it this year. But I want to show you one of the videos that the kids get to see, and it does show off some of our solar instrumentation here at Griffith Observatory. So enjoy this little clip, and I'll tell you a little bit more about that school program and how we're using the instrumentation here virtually, just like you saw now.
At Griffith Observatory, we have two instruments that use the sun and its motions to indicate time throughout the day and throughout the year. Sundials tell time using shadows and the apparent motion of the sun. Our sundial was designed to tell time with a wire aligned exactly north to south. As the sun arcs across the sky in its daily motion, the wire casts a shadow that moves across the marks on the bronze ring. Sundials let us see the rotating Earth as the fundamental timekeeper. Griffith Observatory's Gottlieb Transit Corridor is an outdoor public instrument used daily to observe the sun. While it is similar to instruments from ancient temples and medieval churches, it has a modern update. 4 primary components make up the instrument. A bronze line runs exactly down the center of the corridor from north to south. This is a meridian. The line is met by stairs on the north side and a black monolith on the south side. Mounted to the top of the monolith is a metal panel containing a hole. As the sun moves across the sky each day, the hole sends down a spot of the sun's light across the walls and floor of the corridor. The meridian arc is at the south end of the corridor. Each day when the sun reaches its highest point in the sky and crosses from the eastern half of the sky to the western half, the spot of sunlight moves across the meridian arc. If you watch this once a day, every day, you begin to notice that the sunlight does not cross the arc at the same place each time. The meridian arc demonstrates that the sun passes higher in the sky during the summer and lower in the sky during the winter, and it indicates the month, day, and season. Then, when the spot of sunlight crosses the arc, it activates a special map of the stars, the ecliptic chart. Our ecliptic chart doesn't just plot what stars are in the sky, it also shows us what the sun's light blocks from our view and where the sun is among them. Throughout the year, the sun appears to pass through the zodiac constellations, which are also marked along the meridian arc. This change in the sun's position is caused by the Earth's orbital motion around the sun. With just a spot of sunlight, this instrument is able to reveal how the sun's progress through the stars is connected to our calendar.
I feel like I should thank our museum guide for presenting that so wonderfully, Sarah. Again, this is all part of what we're doing to bring Griffith Observatory online, and the video you just saw is part of our new online school program. This is being run and operated, of course, by the City of Los Angeles Department of Recreation, Parks, and Griffith Observatory, but it's also being funded by our foundation, the Griffith Observatory Foundation, which is our public nonprofit partner in a lot of this. And it's through them that we're able to reach so many students. They help us operate the in-person program, and indeed, we can't do it without them. So if you like this sort of thing, you want to help bring it to kids, you can help get involved is all that I would really say. I know a lot of folks, their first visit to Griffith Observatory was when they came in a school bus or they came as a kid with a class. Now, with restrictions, a lot of classes, still won't be coming back. Obviously, they haven't been now. So we stepped up and we created an online program to bring the instrumentation you saw today, to bring it to life for these school kids and to inspire them. I saw in our chat, Karen said her son was born on the winter solstice 2013 and he wants to spend his birthday at Griffith Observatory. He's 7 now. And that's exactly the sort of inspiration that we are here for, and our foundation is here for as well. So thank you everybody for joining us, and don't forget, tonight at sunset we have another program for you. Patrick, you're going to tell us about why the sunset has these colors, and you have a nice little presentation for us there. I don't want to ruin what you're going to say now. I'll be out at our sunset lines. We have lines that are marked in our walkway, and we've predicted the direction we think that sunset's going to go. And we'll see whether it actually falls the direction that we expect it to go, whether the scientists and all the folks throughout history making all these measurements figured out whether they're still correct today. I kind of have a feeling they will be. Our meridian arc and the Gottlieb Transit Corridor showed that we're on track so far. So we'll be doing all this tonight, and you can come on back and join us at 6:30 p.m. Right here at Griffith Observatory's YouTube page. We have a separate stream for it already set up. You can follow it. If you've liked this program with us today, everybody that's followed us, be sure to subscribe to our channel. If you sign up for notifications, you'll be told whenever we're doing any of these events. And of course, in the description down below, there's information how to join our foundation, how to get a newsletter, and how to get more from our team, our All Space Considered team. You can see clips from it and all sorts of fun stuff that we have available for you. And be sure to check out our new webpage as well, which works really great on mobile these days. So we're looking forward to the day we can reopen in public, but for right now, we are not open to the public still. So, please enjoy our online programming, and this is how we can engage with you all out there. So thank you so much, and we'll see you tonight.